Hello, welcome to this link live session. This is Sanjeev Gupta. We will wait for 2 or 3 more minutes to give time for other people to join in. And thank you for being here. Okay, so again, thank you for being here. It will be a fast-paced 60 minutes. Actually, 45 minutes I have allotted for speaking time and about 15 minutes for questions. And if your questions do not get answered, if we don't get to them, you are welcome to share them with me by email and I will try to answer them. So as I was preparing for this presentation, what became very quickly obvious to me is that ship repair projects, they are complex, we know that, and they are full of uncertainties. As to why the projects are late, I think we all know why they are late. So instead of just talking about why they are late, I'm going to talk about also how to improve their timelines and timeliness, right? How to do them in a faster cycle time and how to deliver them on time. These are some company credentials, which I'll come back to later, because I think the more important thing is to dive right into the content here. So we know that in a lot of cases, and my work primarily has been with the US Navy here and a couple of private shipyards that do large ship repairs. And there is a big discrepancy between the due date and the actual date. Sometimes you are missing your due date by about 10%. Sometimes you are missing it by almost 70, 80, 90%, especially when you have multiple ships undergoing repair in the same shipyard. And below that, we know that when we did the plan, when we came up with the due date, we did our best to plan out the scope. We did our best to estimate the task times, the best estimates that we can provide for the task times. When do we need the parts so that we can give the information to the suppliers, and then we also take that information back in terms of their promises and put that into the plan. And we also create resource schedules for the resources that are limited. But in actuality, the reason we don't achieve the due dates, it looks like, is because in addition to the planned scope, there's always going to be growth work. You open up a ship up and you find work that you did not anticipate. Or the customer themselves might come back and ask them to add some scope into the project. Same thing with task times. You start executing the task. There are some issues that come up in the task. Things are, more damaged, more corroded than what you thought they were. So it takes a longer time to fix that. There might be work stoppages for a variety of reasons, from as minor as availability of paperwork to availability of materials. And there might also be some inefficiencies in terms of how people are doing their work. Similarly, we have a planned availability of part that we're into committing our due date, but there are supplier delays, there are internal delays that happen, in terms of paperwork delays, decision delays in terms of procurement of parts. And same thing with resource schedules. We came up with resource schedules, we did our best, but unplanned resource shortages occur for whatever reason. Then there is non-instantaneous availability of resources, which means that overall we have enough resources for the month, but on a day-to-day basis or a week-to-week basis, we don't have the resources exactly in the profile we need them. And if you have multiple ships undergoing repair, this is pretty common. There might be changes in ship priorities. Something else becomes much more important. It comes and displaces all the work. Now, this is the reality of ship projects in my mind, right? So if we try to do a root cause analysis here, probably this is where we will end up with, and then we'll try to find solutions to these problems, right? So really the thinking that we have is that projects are late because the real world is not perfect. Therefore, For projects to be on time, we have to make the real world more perfect. Right? This is what underlines most of our thinking about how to improve delivery of ship repair projects. And this is kind of what what is happening is there are these real world imperfections, whether it's in terms of changes, delays, internal delays, external delays, decision delays, all kinds of delays, funding delays. And then there are limited resources, which get exacerbated by non-instantaneous availability of resources, unplanned resource shortages, etc. So therefore, the direction that we normally take is let's do a better planning and let's do better execution. Better planning kind of falls into generally three categories. There will be more, but three major categories. Let's do better job at scoping. Let's try to do predictive maintenance. Let's use all kinds of AI. Now there is a big talk about AI. Let's use all kinds of systems so that we can have much fewer surprises in terms of growth work when we go into execution. Similarly, let's do a better estimation of how long something will take, better estimation of the commitment dates from the suppliers. And let's have more experienced planners who can spot any weaknesses in planning quickly, make sure there are no blind spots, and they can bring all their experience to bear so that now we have a more perfect plan. So really what we are doing is to make the world more perfect. On the one side, we are trying to do better planning. On the other side, we're trying to do better execution. So this gap that exists between planning and execution, we're trying to close this gap from both sides. In terms of better execution, general thrust is, of course, better visibility. If we just know what is going on, we will not get blindsided. We will be proactive. That is the general thinking. So let's just get more visibility. More visibility meaning more real-time visibility, more detailed visibility of exactly what is going on. Better supervisors who will not let things slip. If there is a small delay happening, then they will be proactive, follow up with whoever to make sure the delays don't happen. If they're not getting enough resources, they will hound whoever is responsible for resources to get resources. And better governance. Better governance is huge in terms of the thrust of current improvements efforts. One is better governance in terms of customers. Let's make sure that customers give their approvals on time. Let's make sure that customers don't change the scope in execution. Suppliers, same thing. Let's have suppliers have late delivery penalties, for example, or internal metrics. All kinds of metrics are put in to make sure that everyone is held more accountable. So better visibility, better supervision, and more accountability. That is the general direction. But this has been going on for 40, 50, 60, 70 years and does not make an impact. And I think that is the main point, that we cannot make the real world more perfect. Yeah, we can improve scoping somewhat, but if we improve scoping, maybe our estimation still suffers. Even if we improve the scoping fully, you are not guaranteed that the scope will not change in execution. No matter how good your estimate is, reality will always be different. Right? And this is the real world. Because again, it's not just that the ship projects are complex. Uncertainties and variability is intrinsic to ship projects. So we just cannot keep pursuing this direction of making the real world more perfect to bring in ship repair projects on time. We have to follow a different direction. And the direction I'm proposing that we explore is, can we significantly reduce the impact of these real world imperfections, of resource shortages, of changes, of delays, but without adding time or resources? There is one way to remove the impact of real world imperfections to deliver ships on time is to just promise a due date that is further out. But that doesn't solve any problem. The customer needs their ship back when they need them. Similarly, adding resources, the cost is what it is. There are already cost pressures. So we cannot just say that to deliver the ship on time or faster, we have to add more resources. We have to make do with whatever time and resources we have available. In fact, we have to do better than that. Right? So how do we reduce the impact of these real world imperfections, but without adding time or resources? And that is the direction I am going to follow. I'm going to try to explore in this webinar. And for that, I'm going to take the discussion forward in a kind of a structured way. I will start with a scenario of a perfect world, and where the resources are available as needed. There are no delays, no changes. Let's see what is a good way to deliver on time in such a perfect world. Then we will add the effect of delays and changes, whereas resources are still available as needed. Then we'll shift to resource limitations, quadrant 3, where we will say there are no delays or changes, just resource limitations. And then we will add all the complexities and look at the real world scenario. And what the objective here is to identify, is there a way, and specifically, is there something in the way we schedule projects, in the way we schedule resources, in the way we schedule activities? Is there something there that can minimize the impact of resource limitations and delays and changes? And how much better can we do? So to start with, this is a very simple illustration I've drawn up. You know, ship repair projects, the ones we have worked on, are sometimes 6 months and sometimes 4-year long projects with somewhere between a few hundred to 100,000 activities in the project, right? And generally, you open and inspect a ship, then you start doing the repairs and various other things that you need to do. After the repairs are done, you put things back together and the ship is out, ready to go. But for this discussion, I'm going to focus on the colored part, because I think that is where the scheduling complexity is the highest. And whatever scheduling complexity inefficiencies you have in this part, they flow back into the rest of the project. So let's see what will happen in such a ship in a perfect world. So what you see is each of these activities, circles is an activity. Blue, there are 4 blue activities. The first blue activity takes 9 days and so on. And the last one, B4, takes 6 days. There are 2 green activities. B1 and B2 have to be done before the green activity can be performed. So think of it like, if you are, the purple activity might be installation of a cooling system. And for installation of a cooling system, you need pumps and the valves installed. And for pumps, you have to repair certain components. And for the valve, again, you have to repair some components. And if you were to be asked how long this part of the project would take, the plan would be 28 days, right? Because all you will do is you will calculate the longest path, and which is in this case highlighted by the red circles. And this is the plan, and the actuality is 28 days. And over here, scheduling is critical path method. Control, so critical path method was invented in 1959, or at least the formal paper was presented in 1959. And it was invented in the Navy as well as in DuPont simultaneously. The control of earned value, this came about in 1961 through a Department of Defense policy. And that is your primary method, because what we are saying is, now we have created a perfect schedule. We need to make sure that people are not inefficient. So that is where the concept of earned value came from. And this works. If the world were perfect, this is all you will need. You will lay out the activities, find the critical path. And as long as people are not lazy and they're not inefficient, your plan and actual will be the same. But now let's introduce what happens when delays and changes happen. So we're going to introduce big delays and big changes. And the impact of all that is felt in the form of ultimately delays. So let's say there is a scope change on activity B1. As a result of that, instead of 9 days, it takes 12 days to finish. So 33% delay here, 100% delay on activity B2, 67% delay on activity B4, and a minor delay on activity G2, and so on. If we were to be asked, what is the net impact? We'll again look at what is the critical path after the fact. And we say, okay, the critical path changed during execution, and the actual is 30 days. And therefore, right when the critical path was invented, at that time, people were aware of these uncertainties. And what they suggested was not just use the critical path, but also PERT. PERT is essentially about during planning, not just coming up with one estimate for each activity, but 2 or 3 estimates, so that we can understand what is a reasonable due date that we can promise to the customer. And again, this would work just fine if all you had was delays and changes. Now, the important thing to note here is most of the delays and changes don't matter. All these delays and changes, the project had only a 2-day delay, but that does not match our reality, our experience. In experience, what we find is every small delay seems to have a big impact on the project. Everything that is delayed seems to carry over to the end of the project. And this is what leaves management wondering, why does every delay and change matter? It should not. But it looks like every time we have to analyze why the ship was delayed, we find all these 100 reasons where the delays happened, and we said this is the reason ship was delayed. And that is also the experience on the front line, that everything seems to be critical in execution. We will analyze why that is happening, but just make a note of that for now. Let's go back to critical path planning and scheduling. I would highly recommend, because there's a lot of confusion about critical path. Some people complain that critical path is not a scheduling technique, so it's just a planning technique. Some people say it is a way of thinking. But instead of listening to all that, I would rather go back to the source. This is a paper published in 1959. This is available on the web, and I can send you a link of this also, by the inventors of the critical path. These were the people working at DuPont. And really, it highlights what they said. They said we need a schedule so that people can work on the right things at the right time. And we need all this information to create such a plan. And the question they posed was that to what extent can we use such a method in a software to prepare a master schedule, to revise the schedules, to meet the changes and delays as that happen, and to keep everyone advised of what the project progress is. So this is fine. And I think critical path would do a good job in these areas if it were not for the resource issues. So what the same authors in the same paper, on the 7th page of their paper, they said that this method does not consider available equipment and manpower. All these schedules are technologically feasible, but not practical. I think that's the key statement. Even the authors, the inventors of critical paths, realized that they were not able to handle the resource limitations. And they said that is why this is absent. And they also mentioned that if we have a resource constraint, then we have a large number of possibilities in terms of the scheduling. So let's go there. So let's say that you have resources that are limited. And for the first 4 activities, blue activities, instead of being able to do all the 4 of them in parallel, you have only 2 blue resources. These blue resources could be individual people, could be crews, whatever, right? Whatever defines your resources, could be equipment. But you can do only 2 of them at a time, not 4. Similarly, you can do only 1 green activity at a time and 1 purple resource, which is fine. In just such a simple case, there are 12 possibilities for scheduling. How would you go about scheduling this? So maybe even though critical path method does not incorporate resource scheduling, what is wrong with just using critical path to allocate resources? Why don't we just calculate the critical path, the second most critical path, and use that logic to allocate resources? So we'll say, okay, since this path is the most critical, our first blue resource out of the 2 will go on activity B3. And the second blue resource will go on activity B1 because that is the second most critical path over here. And as a result, my overall schedule of the project will be 40 days. Right? This is what would come out. But remember, there are 12 possibilities here. And does critical path give us the best answer? So in this particular case, sometimes it might not. But in this particular case, what you see is the range of outcomes that is possible is 34 days to 40 days. I think this is significant. How we schedule resources has a big impact on how long the project will take. In this case, by scheduling the resources better, we can go from 40 days to 34 days, right? Which is 6 days over 40 days improvement, which is almost 15% improvement in the timeline of the project. And that is one. Number two is the critical path method does not give us the right answer, at least in this case. Sometimes it might have given us the right answer, but at least it's not guaranteed to give us the right answer. So it's not a reliable logic for scheduling of resources. Now, what happens if we have changes and delays on top? So all that happened was critical path changed. And again, the options, the huge range still from 38 days to 46 days. Right? So in fact, the range increased. The range of possible options went from 6 days to 8 days. And in this particular scenario, again, it might be a contrived example, but at least it is possible that in this scenario, critical path did not give us the right answer. And the range is huge. Critical path did not give us the right answer. The number of options that are possible are 12. In a real world project, if you're doing aircraft carrier repair or a large ship repair, the number of potential combinations could be somewhere between thousands to tens of thousands. So does that mean that we just need a super duper software? Is that the solution? We just take all this data, put that into the system. So if the software can analyze a critical path, it can, today's software with all the computing power we have, can also quickly compute all the possible scenarios for resource scheduling, and it gives us the right answer. And in execution, as things change, maybe on a weekly basis, we can run the super duper software again and get the right answer. And what I'm suggesting is don't fall into that trap. Because not only can we make the world, can we not make the world more perfect? This fallacy. We cannot predict how much imperfection there will be in the world. So we can, right? So what will happen is that you will have data issues, you will have unknowns, scope will creep up. And if you just have data issues, what you will find is you bought this super duper software and you're not even able to get it started because you're still caught up in the data cleanup phase. Or let's say, lo and behold, you got all the data correct, and now you're ready to start using the schedules. Unknowns will happen. And as these unknowns happen, again, you need to respond quickly to collect data and put that back into the software, come up with a new schedule, and you will find that the schedules are now volatile. You were asking people to work on a certain set of pumps yesterday, and a week later, you say, you know what, stop that work and work on something else because the second set of pumps has become more critical. It's not going to work. And this is primarily the reason why the frontline people on the ship deck, they don't follow the schedules that are given out by the scheduling department because they cannot. Right? So a super duper software is one more trap that we should avoid falling into. And I want to emphasize this point. With all the talk about digitalization, the power of data, the power of computing, and our thinking that whatever human beings cannot solve, computers are the right answer for that. You can fall into this trap of creating a very complicated scheduling software which can analyze all the combinations. But first, you will buy the software and you will not be able to get started because you will not have the data. Secondly, you will have unknowns that happen. And third is your schedules will be so volatile coming out of such a software that people on the front line will still not follow them. We need, before I get into what my proposed solution is, or the solution that we have implemented successfully in a variety of organizations, I think it's important that I highlight at least what we think are three qualities of a good schedule. Of course, the schedule should be efficient in the sense that with the minimum number of resources, it should be able to accomplish the maximum objective. So if lateness is our concern, then with the least resources, they should be able to produce the shortest timelines. It should be robust. Robust in the sense that even if my data is not good, even if changes happen, even if delays happen in execution, I should still be able to continue marching on the schedule for most part, and still be able to achieve the date that I promised to the customer. And finally, it should be simple. Simple meaning that if the logic of scheduling is complicated, and if people on the front lines do not understand that logic, imagine what will happen. You have a change, something happens on the front line, and they need to respond immediately. So if they have not understood the scheduling logic, or the scheduling logic is too complicated, then the decisions they make will be different from the logic that you are using in your formal scheduling system. So for the two logics to be aligned, which is the logic that people will use on the front line on a day-to-day basis to deal with uh, changing conditions, and the logic that you use in your formal system, for those to be aligned, the logic has to be simple. It has to make sense. Right? So any schedule that does not meet these three criteria, in my mind, is not a good schedule. Now, in a world of limited resources, it's for you to judge. Does critical path give you the right answer for efficient scheduling? We already saw that it does not. Does it give you a robust schedule? We saw that it does not. In fact, it makes things worse, which I'll show you later. What the critical path does is it actually creates schedules that are very brittle. Because really what keeps up happening is that when you use the critical path logic, so you schedule your resources in the most critical path, then you move out the activity on the less critical path. But as a result of that, you're eating up all the slack that is on the non-critical path. So as the slack gets eaten up because of limited resources, you end up with a schedule that has almost, for practical perspective, no slack, and the schedule becomes very brittle. Any small delay or change suddenly makes a huge impact on the overall schedule of the project. So it does not do that either. Is it simple? The basic critical path is simple, but when you try to account for limited resources in a critical path schedule, the only way you do that is by adding complexities into your schedule in the form of either extra constraints, extra dates, extra dependencies in your project plan to make the schedule come out the way you think the resources should be leveled. So it's not simple either. And as a result of that, what keeps up happening is that you have a schedule, even if you have a big scheduling department and your schedulers feel that they are doing an awesome job of creating the schedule is practically unusable on the front line. Let's go to what I think is the scheduling logic, which we have seen work. If you look at the left side of the picture and the right side of the picture, our best options over here were these options 1 and 2, both in execution and in planning. That these were the best options. And there is something common in these best schedules. I am calling this mode B. These are 2 of the 12 options, and 10 of the 12 options are not good. And the main difference here is that in the mode B, what you're doing is you're taking your limited resources. Since you have only 2 blue resources, you're not looking at scheduling the resources based on the critical path or something else. What you're doing is you're looking at downstream activity, the integration point, and saying, okay, how many integration points can a blue resource support? And the decision is very simple: either allocate them to the first green point circle or allocate them toward the second green circle. Versus over here, your resources are scattered across these integration points. In this case, what you see is that half of my resources go on the top part of the project, half of the resources go on the second half of the project. But when we finish these two activities, it doesn't matter for the project. The project is not flowing because the green activity cannot start. It is stuck. Right? So what we are saying is simple, that projects are a series of integration points, especially the second 70%, 80%, 60% of the project is just a series of integration points. And these integration points is where the largest coordination losses occur. And the faster we reach these integration points, the faster the project keeps flowing. If we don't reach the integration point, the project stops flowing. And so the main logic is this focus and finish. There is one more advantage of this focus and finish logic. So if you look at the left side of the picture and the right side of the picture, in the left side of the picture, a delay on B1 and a delay on B2, they happen sequentially because B1 and B2 are not being done in parallel. So whatever delay happens on B1, it adds to the delay of B2 and it adds up to the delay of the project. In this picture, the delays, only the worst case delay, which has the worst impact in terms of the critical, that's local critical path, that is the delay that passes on. So this golden rule of focus and finish is also most likely to minimize the impact of delays. It also simplifies planning. Think about it. I had 12 options, but I boiled it down to just 2 options. And this is something that a human being can decide. In a large, complex project, let's say an aircraft carrier with 100,000 tasks, what you will end up with is essentially 7, 8, 10 options maximum. Because remember, the main decision you are making is when to start each work stream. So the only decision is start work stream 1 or work stream 2. Downstream, it will follow whatever you started. So if you look at that and you look at the common resources, you don't have that many combinations available left. And this decision about whether to start work stream 1 versus work stream 2, I will not leave it to the software, because it's not just how long each of these streams takes, but there might be additional considerations. Technically speaking, theoretically speaking, I might have this work stream that is shorter and this work stream that is longer, but I might have a higher risk on work stream 1. So the decision of whether work stream 1 should be started first or work stream 2 should be started first is a management decision, is a management judgment. Similarly, you might have some other consideration in case you are doing repair for an external party, which is how do you get paid? So what is the cash flow impact? You might also have considerations about resource contention with the other ships that are going on in the shipyard. So this decision should be, at the most, I will say that the scheduling logic, it cannot be completely automated. Computer assisted scheduling is the way to go if you want to use focus and finish. There are 80% of the cases of this focus and finish boxes. So these boxes that I drew, I'm calling them focus and finish boxes. 80% of these cases are covered just by this idea of integration points, assembly points in a project. The other 20% are covered by these 3 cases, interactive work. So for example, if you have complex repairs where you need multiple trades, so you don't want to schedule those activities independently. Those schedules should be together. And the way to do that is to schedule the box rather than the individual circles. Same thing in outfitting or integration and testing. Or when you have iterative work, one example of iterative work is you're doing some investigation, you try something, it doesn't work, you try something else, and you get done when you get done. So that entire iteration should finish before you move on. You should not schedule the circles, you should schedule the boxes. Or approvals, you might have an approval cycle where you find some problem, you need to give it to the customer sends back some questions. So that entire cycle should finish very fast, instead of us doing our job, sending it to the customer being busy with something else, then taking their own sweet time to respond back, and then being caught up with in back and forth loop. And clear work fronts, especially if you have different contractors, coming in to do different parts of the work, or in the case of uh, 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 the defense ships, you might have nuclear work and non-nuclear work, where you want to provide clear work front to the nuclear work so that they can come in and do their work. So again, you draw the boxes based on that consideration. What is the impact of these boxes? The impact of these boxes, so I'm going to go from a baby project. So this project that we looked at was a baby project. I'm going to go from a baby project to a slightly bigger project, but still not as complex as a real project. But this is just to illustrate the benefit of how we use focus and finish, this map meaning these boxes, for resource leveling. So the scenario here, this thought experiment, just uh, stay with me, is we have three different work streams. There's a set of dots here, circles here, which will take 5 weeks to finish if we have all the resources available on the first work stream. 7 weeks after that, 4 weeks after that. And if all the resources were available for all the work streams, our project would take 16 weeks. But we don't. We have less than ideal number of resources. We have only resources to support only about one work stream at a time. So what happens when we use the critical path method to go down and start scheduling the dots versus focus and finish? Let's look at that impact. So mode A is when we are scattering our resources across the three work streams and using the critical path scheduling. And what we find is, yeah, we are able to gain some efficiency in the sense that instead of taking 5 weeks plus 5 weeks plus 5 weeks, 15 weeks, we are able to get it done in 12 weeks. Similarly, instead of 7 times 3, we can get it done in 18 weeks. 4 times 3, we can get it done in 10 weeks. And we also have some overlap. We can start some green work before all the blue work is done. Right? So there is also some overlap. As a result, we get the project done just from a planning perspective. We are not in execution yet, in 37.5 weeks. Versus if I use focus and finish, look what happens. So I'm a little bit seemingly in planning more inefficient. I'm saying we will not start the next blue box until we finish the first blue box. That is the meaning of using focus and finish for actual resource management, resource leveling. So we drew this focus and finish box and we said we'll finish this box before we start the next blue box, and so on. Same thing for the green boxes. Now look at what happens. Overall, my project duration has come down to 30 weeks. Why? It seems like focus magic, but the logic is simple. We are able to start the green part of the repair project much earlier. So in one of the examples we had was, this was submarine repair. So previously this was small repairs. So previously the project was taking about 45 days, and all the integration and testing would start happening on about day 37, 38. And then there would be a lot of scramble. When we implemented this focus and finish idea, the testing began to happen from day 12, and the project duration came down from 45 days, I think, to about 33 days or something like that. One more interesting thing that has happened, which is the amount of data that I need, the accuracy of data at the dot level versus the accuracy of data at the box level. So I need less accuracy in the details and just enough accuracy in the aggregate. So I can produce good schedules with less data or less good data. The next thing that has happened is you see these gray boxes, gray hatches. So this is the buffer. In the top schedule, there is no buffer. A small delay, we ate up all the slack as we optimize our resources. And a small delay on work stream 1 means the delay will propagate to work stream 2, which will propagate to work stream 3, and it will affect the entire project, and there's no slack in the system. Over here, because of focus and finish, not only did we consolidate the work into smaller duration, we also consolidated the slack into buffers. And also, my critical path or the longest path. I don't want to call it a critical path because you also have the resource leveling that's going on. So the longest path is going to be much more stable. Any small delays and changes here, most of them don't matter. Only the aggregate impact of that will flow into the green box. Only the aggregate impact will flow into the purple box and the next green box. And there is enough buffer here anyway, so that a delay on the blue box will maybe delay the blue box will not, but will not affect my longest path here. So I have a much more stable schedule. Right. So we already talked about it, but where the buffers come from. But think about how these buffers can now be used to manage resources in execution. Because it is one thing to create a schedule in planning, but in execution, and delays and changes are happening, your schedules need to be adjusted, but without redoing the entire plan. So what these buffers allow you to do is something simple. You just monitor the rate of consumption of the buffers. And if you have to make a choice between allocating resources to this blue box versus some other blue box, you just look at which box has the buffer that is getting depleted at the fastest rate in front of it. And that is what gets a priority. Right? So the rate of buffer depletion becomes a metric for resource allocation. And the same rate of buffer depletion becomes a metric for project control. If my buffer overall is getting depleted at a faster rate than the rate at which work is happening, I know my project will be late. Right? And these metrics are useful and meaningful because my underlying schedule is much more stable. If my schedule kept changing, none of these metrics would matter, because tomorrow the metrics are telling me something else. Day after tomorrow, the metrics are telling me something else if the schedule were not stable. An analogy would be Google Maps. Google Maps works as long as your map is stable. If your map kept changing minute by minute, your Google Maps will not give you the right directions. Impact of delays and changes. If new scope gets added, do you need to redo the entire plan? No, your box remains the same, and you just redo the dots. Your inputs are delayed, fine. You just look at whether it impacts the buffer or not. And so a lot of delays and changes, they get absorbed, number one. Number two, a lot of these delays and changes, they don't mean that you need to redo the entire plan. So to enable this focus and finish logic, you need you don't need a super duper software in the way you are thinking, but what you do need is a software that can help you create this box level plan, which is what we call the resource deployment map. It can do resource leveling at the box level, but the priorities are issued at the dot level. Progress is reported at the dot level, but the control is based on the box level. Right? It's kind of that simple. And now to kind of, just to highlight that this is not just theory, we have worked not just in ship repair projects, but construction projects. We have worked in large construction projects, engineering and product development projects, pharmaceutical drug development projects. The underlying issues are always the same, that you have delays and changes and resource limitations. And how you schedule your resources has a big impact on your timelines. And by the changing the way you schedule your resources, not only shortens the timeline, but also makes the schedules more predictable. And we have achieved success in all these wide variety of projects. And we have won industry awards, the most notable being this Franz Edelman Award, which is known as the Super Bowl of operations research. Right. So beyond that, I'll just leave you to evaluate whether this focus and finish logic, what we call flow-based scheduling, because the idea is to keep the project flowing. Is it efficient? Is it robust? Is it simple? And with that, I will open up the floor to questions. So if there are any questions, please put them up in the box here. And I think we are a little bit running out of time. I have a facilitator here. Let me just ask them if there are Hello, Navneet. Are there any questions? Just send me a message back. Okay. So just let's take a couple of more minutes, and if you have any questions that you think of them afterwards, just email me and I'll answer them. Okay. Okay, so we are also coming to the end of the session here. Thank you very much to all of you for attending, and we will of course share the slides. And if there are any people who want this paper on critical path, I think this is an important paper to read for anyone who is interested in, not just uh, uh, discussions based on opinions, but based on facts. You should read this paper on critical path written by its inventors. Thank you very much.